So I didn't expect to be following up on the video on the Coral DHT so fast, but I managed to get in touch with the authors of the original paper, and they were gracious enough to respond and give us some pointers on what did and didn't work from the time where they implemented the sloppy hash table. And they basically responded with, the technique was clever, but for it to function, you need a really, really, really wide deployment. And effectively, in practice, they saw a situation where nodes weren't actually able to join their clusters fast enough, or at least form their clusters quickly enough to be effective. And I think that really makes sense in the context of like web browser, sort of very ephemeral content fetching style of work, where you're sort of popping in and out. Like it's not enough time to sort of progressively form a set of 3-tiered cluster of nodes. And so the authors recommended that we take a look at another paper that of theirs called Oasis. And the Oasis paper was very interesting. It takes a very different approach to anything we'd seen prior. And this time they basically said, okay, rather than try to reinvent or rediscover the network topology every time we go to make a request, what if we just built an entire map of the internet and started from that as sort of a priori knowledge that you could query some service for to be directed in an anycast fashion. And so the theory here is just there's a piece of internet infrastructure missing. We need to provide that infrastructure so that nodes can dial each other very quickly, or at least be very efficiently routed to the proper node to fulfill a request. And while that was really interesting and exciting, it's a big undertaking. And I looked at this, the Oasis project, and in our line of work, we're really excited about this sort of empowering stuff at the edge style of research. We want to see systems that can be deployed in a highly distributed fashion that work really well on a thick client model where the capabilities on your device are really elevated and ideally as high as the capabilities on a cloud server, modulo compute power. There are some elements of the Oasis paper that really jumped out. And the thing that really jumped out at me was first the performance of this Oasis system that they built, which I'm not going to go into, is pretty incredible. But the other thing was what they had honed in on as a useful technique for doing this triangulation in the first place. Because to build a map of internet latencies, you have to actually go probe those latencies and do the discovery in the first place. And the system that they used and built upon was a system called Meridian, which is the subject of today's conversation. Meridian is a lightweight network location service without virtual coordinates by Bernard Wong, Alexander Slivkins, and Imgun Sirir. Pardon me if I'm butchering the names. But if you look at this chart, Meridian's jumping out as pretty successful, and it is a dynamic network discovery tool. I'm not going to get into parsing what these performance charts mean exactly, but in doing some research, I looked at this and said, okay, these are exciting figures. I really want to understand how this Meridian tool does what it does in terms of mapping its understanding of determining efficient latencies through the internet. Okay, so what does Meridian do for you? Meridian gives you fast paths to other nodes. It's going to help you understand how to efficiently stay connected to the peers that have the best latency and give you a sort of location approximation that is based on latency. And so it's optimizing for the metric that you're actually trying to reduce anyways. How it does it is really, really, really neat. So let's get into that. The first thing to understand about Meridian is it is not using the clustering technique that we examined in the Coral DHT paper. It's using a ring configuration. And rings are concentric, non-overlapping circles radiating from a node measuring latency. And so there's a couple of bits here that we need to sort of talk about, but like basically you can sort of think about this as bracketing each of these rings. So we have ring 0, ring 1, ring 2, ring 3, ring 4, ring 5. Ring 5 has a max latency of infinity. So everything is going to end up in ring 5 if it doesn't meet the threshold for the outer threshold for ring 4. And we have a couple of constants that sort of drive the configuration of the whole system of rings. There is a constant for the time in milliseconds. Then there is a multiplicative increasing factor, which they've subbed in as 2. There is the clamping constant, so just basically how many rings are you going to have. In practice, the test runs of Meridian used 9. For some of these examples today, I'm going to use 5 because it's a smaller number and easier to put on a diagram. And basically, just to run a simple calculation for what the inner and outer ring radius of ring 4 is, I've sort of done out the math out here. So subbing in some of these constants that are chosen on the left, ring 4's inner radius is 1 millisecond times 2 to the power of 3. And because that is going to be the same as I, which is 4 in this ring iteration, minus 1, so 3. And then the outer radius is going to be 1 millisecond times 2 to the power of 4, because the current iteration is 4 of the ring. And so that gives you between 8 and 16 milliseconds. And so the property to note here is our rings that are smaller are very tight in terms of latency. Everything 1 millisecond below, specifically everything of this constant alpha and below, is going to be inside ring 0. And then ring 1 is going to be like 1 millisecond in time. And so it's only going to have a 1 millisecond span, but ring 4 has a 8 millisecond span, and ring 5 has anything higher than 16 millisecond latency in terms of its ring span. So when you discover another node, when node A discovers node J, it is going to do a distance calculation. This is going to be literally just ping node J, measure the time it takes to come back, and that round trip time is going to be 14 milliseconds. And that's going to put it in a ring 4 because it is more than 8 milliseconds and less than 16 milliseconds. Not too complicated. Now, you're going to discover lots of nodes. So there has to be a maximum number of nodes per ring. And this is sort of very akin to the bucket sizing that you will see in Kademlia, where you need to pick sort of a maximum windowing of the total number of nodes that you want to deal with. In this example, I've chosen 5 for the maximum number of nodes per ring, and it's constant per number of nodes. So each 0, 1, 2, 3, 4, 5 would have up to 5 nodes in it. In addition to those 5 nodes, there is another sort of QL of candidate nodes. So you'll accumulate nodes, you'll calculate their distance, and you'll say, hey, you're not part of my ring squad yet, but I'm thinking about putting you in there, and we'll see why that's useful in a bit. But that number K is constant, and the paper recommends, through proofs that I'm not going to go too deep into, that it should be possible to use log of the number of nodes in the network as the K value. And so what that means is you should be able to use a number like 6 for a 1 million node network. So these are really low overheads, right? In practice, though, the authors used numbers. What did they use? 16 nodes per ring and 9 rings per node, to give you an example of what it looks like in the real world. Ring management. So you're going to do latency probes. You're going to find a whole bunch of peers. You're going to put them into rings. You're going to assign that. But then inside of those set of candidates, you're going to do everything you can to maximize the geographic distribution to spread queries across within a ring. So going back to ring 4 here, you really want those 5 nodes that you've chosen to represent the widest range of geographies you can possibly get. Again, you only have the latency number to work with here. And so this is going to be reevaluated pretty continually and is independent of any queries that you're serving as with your selected set. So you can imagine sort of like pick an interval. Every minute, you're going to probe again and sort of try to maximize each ring's geographic distribution. Now, how do you, the first thing that jumps out to me is, okay, well, how do you maximize geographic distribution if you only have latency as your number? To build this out, nodes are going to build their own coordinate space internally, but that coordinate space is not going to be shared with other nodes. It's just going to be used as a local calculation to determine which nodes are in your ring. That is exciting to me and a property that I really like to see in distributed systems, where it's just, hey, we're building this local knowledge. We're going to use the results of that to determine who we talk to, but we're not going to share that out and try to establish any type of global worldview of this. And that's where I think the system is really, really successful. How do they build this coordinate space? And the first time I saw hypervolume of the k-polytope, I kind of had this moment where I'm going to have to decide, am I going to pretend like I know what a k-polytope is and a hypervolume is, and try and sneak one past everybody and be like, oh yeah, totally, no big deal? Or am I going to just admit that the first time I read that, I went, I have an art degree, I don't understand this. So we're going to go with the latter. I did not understand this when I first read it at all. And so I had to do a bit of reading about hypervolumes and k-polytopes. But the thing that's exciting about this, and I think the better way to reduce this, is just membership is organized by the fact that the Earth is round. To sort of get into this, a hypervolume is a type of non-Euclidean geometry. And that's why the paper is called Meridian. The whole sort of linchpin of Meridian's approach and why it believes that it can get more accurate location estimations is that it's using non-Euclidean geometry. And while that may sound like it's very expensive to calculate locally, there are lovely algorithms, and the paper goes on to point out that these can be calculated in linear time. So we're not paying a massive compute overhead here, but we're using hyperbolic non-Euclidean geometry because the Earth is round. And the idea is your latency shouldn't assume a straight line from point A to point B, because that would go through the crust of the Earth. It should curve, if I understand this correctly. If I'm wrong here, someone please correct me, but I'm pretty sure I'm not. So neat, Earth round, and I get to get on the internet and say hypervolume of the k-polytope and pretend that I know anything about what that means. Moving on. What does this mean in practice? You're going to have, let's just examine ring 4 as a set. And so we're going to have K, the set of nodes that are currently in your squad of ring 4. And then you have L, a set of candidates. And you have yourself, which you're going to use as an origin. And you're then going to calculate the hypervolume of the set of K using your origin as a fixed point, and you're going to get a number like 8 for the given set. What you'll do then is iteratively try to sub in combinations of L to find the highest volume you possibly can. And the highest hypervolume you can come up with is the highest geographic diversity that you can possibly simulate, given the nodes you have on hand. And so you may drop nodes or swap in from L to K based on what is the most optimized set that is geographically diverse. We'll get into why in a bit. Specifically, now, what can you use this for? The coolest thing you can use this for is for closest node discovery. And this is going to take a hot second to get into, but this kind of blew my mind when I sort of walked through it and fully understood how this functions. So the first constant, we need to introduce one more constant, which is the acceptance threshold, beta, which is basically going to be for every time this whole process hops, how much closer do you want to get to the answer? And we'll see how that works. And so just to give a basic example, we've got node R here, and node R is going to start by issuing a request to node A saying, hey, find me the closest node to T. And so this is T, and R knows where T is because R can just ping T. Again, all of this is happening through pings. And R probably knows T's IP address, whatever. R wants to know who's close to T. A can then do the following. A will first ping T itself and determine its distance to T. Maybe you could look that up from cache. You probably want to just ping it. And so we're going to send a ping. Let's pretend you get back 12 milliseconds. The next thing A is going to do is it's going to simultaneously ask all the nodes that have between 6 and 18 milliseconds of distance, which is calculated from this acceptance threshold, which is a globally set parameter. Hey, go ping T. And so F, M, and L are going to go ping T and report back to A the distance that they got. From there, A now knows what to do, which in this case is forward this find closest node to M, because M came back with the shortest line. And so then this whole process kind of recurses, and M becomes the center of the universe. And M is going to send out a distance probe itself to T, find some threshold number. And what will likely happen here is M's distance to T will likely be less than the threshold times, what will probably happen is A will discover that M's threshold is less than T if it's less than 6 milliseconds, and A can just respond that M is in fact the closest node. So yeah, you have a match. But if not, if let's say that M comes back with 7 milliseconds, A sends the request to M, M goes to Q, R, and a mislabeled R, and they all ping T, and M gets the shortest number. So it says, okay, cool, I'm the closest. And M can respond to A, and A can respond to R with M. That's really cool. I don't know that I'm fully like conveying how this is working, but like with only latencies and the advantage of being able to ask multiple nodes to ping the same node, we can triangulate. Isn't that cool? Just sometimes, it's just so neat. And the claim of this paper is that by doing these local simulations of non-Euclidean geometry, you are getting a better and more accurate picture of the trajectory to begin with, of geometric distribution to begin with, because you're not introducing these sort of simplified Euclidean planes. And you're going to get really fast stuff. And again, like looking at some of the numbers for this, like this thing is really good at identifying who is close. And so when comparing this to the Coral paper, I think the thing that's so exciting is this concentric rings is so much more efficient than signaling the clustering to everybody, right? We now have this like really nice, clean, hey, I'm just going to ping people and put them into buckets. And the construction of the rings themselves all happens at the process start time based on configuration, right? And at that point, it's going to be a lot easier to do all of this work. So you ready for the bad news? I'll put up the slide that says Byzantine faults on it, and we can see how this kind of limits its effectiveness when used in the wild with peer-to-peer systems. Basically, for this technique to work, you need to be able to trust the latency numbers that other nodes are giving you. And there's very little that will stop them from being able to lie about it. In the context of closest node finding, node A is going to ask nodes F, M, and L for their latency numbers when trying to ping node T. And whatever those nodes respond with, node A has to kind of take them at their word for it. And that's really where this all sort of take you at your word for it. Some people believe that that's really not a useful thing. Some systems don't have that problem at all. And so it really is use case dependent. But if you're talking classic, hey, we need to build a system that is resilient to other nodes in the system lying to us, there's very little that we have right now that will let you get around someone lying about a latency figure. I think the reason I wanted to talk about this was really starting to drill down on this locality problem and thinking about the issue of communicating who has what records quickly. Looking at this Meridian paper, I have some hopes and dreams around the way that we could better organize our peering to prioritize using something akin to this ring system and latency measurements to help make better decisions about whom to keep connections with and about how to move around and triangulate where we are. One of the biggest issues we need to grapple with if we're going to speed up peer-to-peer communication system is to really start to get a handle on how we organize according just to the actual physical topology of the world, right? And so I have some hand-wavy thoughts about how we might do sloppy, gossipy systems on top of this. But I think this was a really exciting paper. There's a bunch of things I didn't cover, like how the actual set membership works. There's a gossip protocol in this. There's also a really interesting sort of like rundown on the maintenance overhead. The maintenance overhead on this is really small. And by maintenance overhead, I basically mean like what is the cost of maintaining these rings and these peers. The other thing that the authors point out is you can use this to target and work with systems that don't support Meridian at all. You can just hit HTTP servers. Anything that'll let you ping it and determine the latency, you can triangulate around that, which is a really exciting additional property. So this is kind of hopefully a building block to some more research, but what I really wanted to quickly do was touch upon an alternative model to the Coral method and something that the Coral authors themselves sort of turn to as a mechanism for doing faster mapping of latency sensitive stuff. So when we're talking about locality, I think this Meridian paper has a lot to offer. Cool. Thanks a lot.